Dear students, in last class we compared electrical circuits and magnetic circuits, and then we studied laws of electromagnetic induction. In today's class we will be discussing types of induced EMFs. There are mainly two types of induced EMFs. First one is statically induced EMF and second one is dynamically induced EMF. In statically induced EMF we are having again two types of EMFs. One is self-induced EMF and another one is mutually induced EMF. Now we will take these types of induced EMFs in detail. Now we shall study what is statically induced EMF. An EMF induced in a coil due to change in flux linking with it but not due to relative motion between the coil and magnetic field. So here EMF is induced in a coil due to change in flux linking with it, but that change in flux linking with the coil is not because of relative motion between the coil and magnetic field. It means that coil and magnetic field both are at rest. In statically induced EMFs we are having two types. One is self-induced EMF and another one is mutually induced EMF. First one, self-induced EMF. To understand what is self-induced EMF, let us first consider a coil and the magnetic field produced by the coil. Now in this coil we are having n number of turns and this coil is supplied by a voltage source V, and there is a variable resistor connected in series with voltage source and coil to vary the current flowing through the coil, and here is ammeter to measure the current. If we vary the current flowing through the coil, then there will be variation found in the flux set up by the coil, because flux produced by the coil is proportional to current flowing through the coil. Because of variation of the flux produced by this coil, which is linking with the coil itself, there will be certain induced EMF in the coil, and that induced EMF in the coil is called as self-induced EMF. It is called self-induced EMF because EMF induced here is due to variation in the flux produced by the coil itself. Now we will write the definition of self-induced EMF. EMF induced in a coil due to variation in the flux produced by itself is called as self-induced EMF. Self-induced EMF is given by E equal to minus N into d phi by dt, and it is also given by E is equal to minus L into di by dt. Here N is number of turns in the coil and d phi by dt is rate of change of flux that is linking with the coil. And in this expression for self-induced EMF, L is the inductance of the coil and di by dt is rate of change of current flowing through the coil. Now we will study mutually induced EMF. To understand mutually induced EMF, let us consider the two coils placed very close to each other. The details of the figure are as under here. N1 and N2 are the number of turns in coil 1 and coil 2 respectively. Phi 1 of t is instantaneous flux produced by coil 1 I1 of t is instantaneous current flowing through coil 1. Phi 12 of t is instantaneous flux linking coil 2 produced by coil 1. Remember here, all the flux produced by coil 1 may be linking coil 2, or all the flux may not be linking coil 2. Only part of the flux produced by coil 1 may be linking coil 2. So here we are calling the flux produced by coil 1, its part which is linking with coil 2, as phi 12 of t. R is resistance variable. It is to change the current flowing through the coil. V is voltage applied to the circuit. In addition, you can see here ammeter A to measure current I1 of t flowing through the coil 1, and G connected to the terminals of second coil to measure the EMF induced in the coil. Now if we vary the resistance R, then current flowing through the coil 1 will change, and because of that there will be change in the flux produced by the coil 1. As a result of that, the flux linking coil 2 produced by coil 1 will also change, and because of that there will be certain EMF induced in coil 2. Let us call that EMF induced as EM, and this EM is now called as mutually induced EMF. Here also you can see second coil is at rest with respect to the magnetic field, but the magnitude of magnetic field is changing with respect to time, and hence mutually induced EMF is statically induced EMF. Now we will write the definition of mutually induced EMF. EMF induced in a coil due to change in flux produced by another coil placed very close to it. Mutually induced EMF is given by EM equal to minus N2 into d phi 12 by dt. Here you have to take number of turns in second coil and the rate of change of flux that is linking with coil 2 produced by coil 1, and EM is also given by, and mutually induced EMF is also given by minus M into di1 by dt, where M is the mutual inductance between coil 1 and 2 and di1 by dt is the rate of change of current flowing through coil 1, where M is mutual inductance between coil 1 and coil 2. Now we will consider dynamically induced EMF. It is EMF induced in a coil due to change in flux linking with it caused by relative motion between the coil and the magnetic field. To understand dynamically induced EMF, let us consider the figure shown here. In this figure we are having two magnets between which a magnetic field is set up. The direction of magnetic field is from N pole to S pole, and in that magnetic field a coil is placed and the coil is named as ABCD. Now if this coil is rotated in the magnetic field, then the flux linking with the coil will keep on changing, and because of that change in the flux linking with the coil, EMF will be induced in this coil, and the EMF so induced E is called as dynamically induced EMF. Here L is length of coil site. Let us say the flux density between the two poles is capital B. In the above figure, if coil ABCD is rotated in the magnetic field, or vice versa. Then EMF is induced in the coil this EMF is called as dynamically induced EMF. For angular velocity of coil in the magnetic field equal to omega radians per second. Effective length of coil site equal to L meters. Flux density in the air gap equal to B Weber per meter square. Area of plane of coil equal to A meter square. Then flux cut by the plane of coil phi is given by N into B into A into cos theta, where N is number of turns in the coil. Theta is angle between the direction of magnetic field and the perpendicular drawn to the plane of coil. That is, if it is plane of coil, perpendicular to the plane of coil, we have to draw a line. Now, if it is direction of magnetic field, when perpendicular drawn to the plane of coil and the direction of magnetic field are at right angles to each other, then cos theta becomes equal to 0, which means the flux linking the coil will be equal to 0. And if this coil is rotated by 90 degree, then perpendicular drawn to the plane of the coil and the direction of magnetic field will be along same line. That means angle between them will be equal to 0, and hence cos theta becomes equal to 1. In other words, flux linking the coil will become maximum. So for this case, theta is equal to 90 degree. But actually, as the coil keeps on rotating, theta keeps on changing. Since EMF induced in a coil is given by E equal to minus d phi by dt, that is equal to minus d by dt of NBA into cos theta. We will substitute for theta here. NBA into d by dt of cos of omega t. Since theta at time t is equal to angular velocity omega into time t, we can substitute for theta equal to omega t here. On differentiating, we get NBA into omega into sine of omega t. Since NBA omega is constant and at omega t equal to pi by 2 radians, sine of omega t will become equal to 1. That is, E will assume maximum value. So we will call NBA omega as capital EM, that is maximum induced EMF in the coil. At omega t equal to pi by 2 or 90 degree, sine omega t equal to 1. So E will become n into b into a into omega into 1, that is n into b into a into omega. Since this is maximum possible voltage that can be induced in a coil, we'll call this as EM. I will close this in box. Therefore, induced EMF may be now written as E equal to EM sine of omega t, where EM is equal to n into b into a into omega. If a single conductor of length L meter is moved in a magnetic field having flux density of B Weber per meter square, with angle theta between magnetic field and conductor axis at a velocity of v meters per second, then EMF induced in that conductor is given by E equal to B into L into V sin theta. At theta equal to 90 degree or pi by 2 radians, E will become equal to BLV into 1, and it is maximum possible value of induced EMF. So we will call this as EM. Therefore, induced EMF expression becomes EM into sin theta. It is for a conductor having linear motion in magnetic field, and the conductor should be moved in the magnetic field in such a way that it cuts the magnetic field. That is, the flux linking with the conductor should keep on changing continuously. Then only the EMF will be induced, otherwise not. Where EM is equal to B into L into V. For this explanation, if you want, you can have this figure here. Let us say this is N pole and here we are having S pole. Between N pole and S pole there is magnetic field, and there is a conductor, and this conductor may be moved inward and outward of the magnetic field. If you assume this pen cap as a conductor and place it in magnetic field this way and move it inward and outward like this, then EMF will be induced in this conductor, because the flux linking with it is changing continuously. Remember, the unit of induced EMF is volts. Here also unit is volts. Dear students, I will stop the class here and continue in next class. Thank you.